Okay, let's get started. So, yeah, first off, thank you so much, Paul and Judy, for hosting the event. I've been speaking. My first DevOps Day talk was with Halifax in Canada about 2 months ago, and it's the actually the first time people host DevOps days like in such a northern Nordic-ish place, and by the time the temperature was great and we had a nice tour and everything. Yeah. And as you can see on my screen, that's intentional. That's the first slide. And because I always have like this debate with my community manager, I think that I should put the title of the talk as the first slide. And she thinks that I should always engage with you first to put my personal profile as a first slide. So I decided to put a blank one. And I think she kind of wins because my first slide is about myself. And yeah, so as you can see, sometimes people can be so self-involved, right? I live in Toronto and my name is Joe. And I'm a developer mostly focused on backend. I like different kinds of databases a lot. And currently I'm working as a developer advocate at a company called Dragonfly. Dragonfly is a multi-threaded high performance Redis replacement. And we're gonna talk more about that later in this talk. In my spare time, I travel a lot, but I travel mostly for two things. The first thing is, those kind of K-pop concerts that are not available here in Toronto. So that's me in Vegas. And another type of travel is for, talks like this, but in person, for instance, the KubeCon, DevOps Days. Yeah, and I like food as well, especially spicy food. I came from a city in China called Chengdu, and it's famous for the spicy hot pot. It looks like this. So if you cannot eat spicy food, the greatest understanding I can have you, as a friend, is that let's order the half-half pot. But I need to remind you that the half-half pot in Chengdu is not actually half-half. It looks like this. So you get a quarter of the pot here yourself as the non-spicy part. Yeah, and finally, I like memes as well, developer jokes, all kinds of jokes. And let's see if I use some of them in this talk. And yeah, as I mentioned, I work for a company called Dragonfly. And yeah, this is the logo I want to have the inception in your mind. And after that, my job is done. But let's get to the real business, right? So the talk today is about optimizing database management in Kubernetes, right? So I will be talking about optimizing the developer or DevOps experience, in terms of how it makes things easy. Not probably some of it, right? But not very focused on like optimizing the performance, right? So, part of it, yes, but mostly optimizing the experience, the platform experience we have. And yeah, as I said, I came from a backend and database background. So if I say things stupid about Kubernetes, please correct me. But I think I have like a decent grasp of it. Cool. So databases, here are a few examples. Some of the traditional ones and newer ones here, MySQL, Postgres. This is the Dragonfly logo that's Redis, and this one is a little bit new. It's actually Volkey, so it's the fork of Redis because of the license change. And they have been doing a lot of improvements in terms of performance and optimization in Volkey as well. They recently announced the released version 8, which is a huge improvement, in this space. And I just want to put more logos here, right? These are all databases. Timescale, if you're familiar, it's a time series extension on top of Postgres. This is Databand. It's actually an open source version of Snowflake. So compute storage completely separated, very strong. Scylla, and this is Polarbase, PolarDB, this is Redpanda, and this is DuckDB. You see the pattern here, right? Like we like animals in this database sector. So they're cute and they're powerful. They're here to not for a sake of change. They solve particular problem. When in like, nowadays people generate what 25 meg. I don't remember exact number, but somewhere around like a few tens of meg data per second per person, consider like all the devices around you. So databases are awesome. Cool. So how to manage them, right? Like we have these awesome tools for different scenarios to store different kinds of data. So how to manage them, right? So this is a little bit beyond me. Like I know I've never seen such a thing called init script. So, but I Googled it. I Googled the history, right? So manually, that's kind of natural. You have the piece of software, and it's kind of like turning on a game, turning on Steam. You double click on it, right? Or dot slash, then the database starts. Later on, they have different configuration parameters that you can use to tune the database and, another natural step, kind of like our backend services as well, right? It takes a configuration file, reads it, and do like adjustment in the system accordingly. And init script, it's something sysv init. As I said, I Googled it. I never seen it before. So I'm not an expert of it, but I heard that it is one of the early days tools that you can use, right? And then systemd is like the dominant tool for managing services on Linux, including databases for a very long while, right? And again, I do backend coding most of the time. I use cloud. So I think in my university time, I've used systemd, not very extensively, but that's the tool we use. So how about yeah, it's kind of like that. Like not that this iPod is bad. It's a great product, right? But you can kind of tell that, we've been like moving the world technology. It's been evolving, but it's still like a gem, right? As a tool. So in the cloud era, what do we use, right? So um, cloud era, like Kubernetes is like one of, if not the most important, but one of the most important tools in the cloud era. And on top of that, we have things called Kubernetes operator to manage databases, right? And then we also have companies and teams like they're trying to build like a uniform data plan for Kubernetes for all kinds of databases, right? One such example is called Kubeblocks. So we're going to talk about these two things today. So yeah, back to database a little bit. So take Redis or Voki as an example. So it is an in-memory data store, normally being used as a cache, right? So sometimes you have some level of tolerance of like losing data if it's not snapshotted, if it's not being appended in time. But that's the nature of it. So what's so hard about it, right? So what's so hard about managing such a software? It doesn't sound like very different from like a stateless app, right? Because it's an in-memory data store. But if you take, as I said, if you take the backups into account, so Redis, Volkey, Dragonfly, we can take snapshots periodically so that, if the process is killed and restarted, then you can load the backup rather quickly. So you have like a rather warm cache still, right? Instead of completely cold cache, right? So backups, restoration, um, it's a software, so you need to deal with version upgrades as well. And nowadays, because of the volume of the data, right, high availability and scalability, both vertical and horizontal, are required. So if we take these kind of requirements into account, then it is not that easy anymore. It's not just like a stateless app that can die and be replaced easily, right? So let's take high availability as example and see what we have before Kubernetes, before operator, right? So there is a project called Redis Sentinel, also by the Redis team. So it is a high availability solution for Redis, right? So itself can be a cluster. I placed one here just to make it simpler, but itself can be a Sentinel cluster as well to provide high availability for itself, right? But the functionality of Sentinel is to kind of be a manager, a high availability manager of the underneath Redis instances, right? So the Sentinel instance, it doesn't do the actual data manipulation. It doesn't provide that kind of service, right? So it's still the real primary and replica Redis instances underneath that does the get set, commands for you. Sentinel is there just as the name kind of tells, as the guard, it provides high availability. And so yeah, that's one example of what we can do if we don't use our Kubernetes, right? So each database kind of have this kind of ecosystem as well. So for scalability, vertical and horizontal, what we have. So you may have heard that Redis is single-threaded. That's only partially true, right? So Redis actually is multi-threaded in terms of like say networking. It also handles the snapshot or AOF, append only file rewrites, in the background. But the most important functionality it provides, the key value data manipulation, that's still single-threaded. So given that, a single Redis instance, normally we wouldn't be able to utilize like the multi-core server. It will be, easy for it to utilize the single core, but for multi-core, it's a little bit hard. That's why Redis has the solution called Redis cluster. But, keep in mind that, as I said, because a single instance can only utilize a single core most of the time, so that means like on a super beefy machine, say if you have 64 cores of some sort of AWS, bare metal machine, right? You need to cluster Redis on that single machine in order to use the hardware. So that's kind of like the drawback. It's all because of the, design decisions back, 15 years ago when Redis was first written, single threaded was kind of the winner choice. Yeah, that's why we're doing things like that today. So it's all kind of historical. So in Redis cluster, you can have like primaries that they exchange information with each other to keep the topology. And each of them, they can have like one or more replicas to provide high availability. Cool. So that's for horizontal scaling and vertical, vertical in the sense that you cluster Redis in that single machine. So this is good, but can we do better, right? So I spent some time talking about the single-threaded nature of Redis. So one thing I need to point out, obviously I work for Dragonfly, but I need to point that out is that first, you need to evaluate your software as well, right? So Dragonfly is compatible with Redis. The API, the commands are the same. If your code uses a Redis client, you don't need to change most of the time. If you're not using like super weird commands, you don't need to change your code. You just point your URL to your Dragonfly, it should work. And Dragonfly is multi-threaded. The architecture is built from scratch, so we don't use Redis code in terms of networking and multi-threading. All the underneath architecture stuff are from the ground up. So Dragonfly, a single instance is able to fully utilize your hardware, right? So to me, I think that's important because, as I said, first you need to evaluate your software first. If you host a single Dragonfly instance on the machine, that will be much easier, than a clustered version, right? So that's one thing I need to mention. Another thing is that, because Dragonfly is highly compatible, Redis Sentinel can be used with Dragonfly to provide high availability as well, right? So let's really take a look what Sentinel does here, right? So it is a instance, Redis instance running in special mode that provides monitoring, configuration provider, and it performs automatic failover, right? So that what actually Sentinel does. Isn't Kubernetes such a great tool to do the same thing, right? Configuration provider, automatic failover, right? And does notification and monitoring. So what we can do is to use a Kubernetes operator to do pretty much the same thing of what Sentinel does. And I see this pattern or not just for Redis, not just for Dragonfly, but in the database sector. That's why we have this talk today, right? So the operator pattern, right? So data stores, they are first off, they're stateful, right? And they need to persist data either in memory or most of the time on disk somewhere, right? So it's a little bit different from the or like it's quite different from the stateless application where I believe our Kubernetes is originally designed for, right? So normally it's the operator is managing the database through a CRD, custom resource definition. And then the CRD, if you instruct it, the CRD will deploy some stateful sets, for the database, right? And some pros for the stateful set, they have stable network identities, right? They can have stable persistent storage, right? And if you code it properly, then you can instruct them to shut down like gracefully in an ordered manner. Same thing for updates as well, right? But on the other hand, it requires more careful planning, right? Because you're taking more things into account. You're running a database right now, not a backend service that you can easily replace that is stateless, right? And each application, they're different, right? Like they're different just, by default. Every kind of databases they have their special requirements. So you need to code the Kubernetes operator kind of for each of them. Maybe some of them are similar, but yeah, you get the gist. So that's really what all, the Kubernetes operator is all about. Let's see some example, right? So let me take you through the Dragonfly operator a little bit. So as I said, it provides, it's a configuration provider. It's able to do automatic failover. It can do scaling like horizontally and vertically. We take security into account. And when you take snapshots like the backups, you can go to PVC or directly go to S3. And obviously, monitoring is one of the important features as well. Cool. So here is the demo. I'm not doing live demo, I'm doing demo in the slide, right? And as you can see here, we are doing like the kind, like the resource type, right? But because we have the Dragonfly operator, once you install the operator into your Kubernetes cluster, then the capability of your Kubernetes cluster get extended a little bit. Before, it doesn't know what is a Dragonfly resource type. It knows services, it knows deployment, config map, replica set, right? But it doesn't know what Dragonfly is. Now you have the operator kind of as an extension installed into your cluster. Then your cluster knows what is Dragonfly kind, what is Dragonfly resource type, right? And those are all the efforts that you put into developing an operator, right? So from this point on, after the installation, your Kubernetes cluster knows what Dragonfly is. Similar deal here, as you can see from here, they are kind of standard Kubernetes API, right? So it's quite familiar. But I need to point out that the replicas, has two meanings, right? It has the one meaning is like what it means within the Kubernetes cluster, right? The second meaning is like what it means for say for Dragonfly or for Redis, right? So replica number of replicas, 3. Normally for your backend service stateless app, it means like you have 3 replicas, 3 pods, right? Like they're exactly the same. But for a database or data store like Dragonfly, 3 replicas in Kubernetes actually means one primary instance of Dragonfly, which handles both reads and writes, and then 2 replicas that's replicating the data from the primary instance. And they won't accept any write commands, but they are able to serve the read commands, right? So even though they're all replicas in Kubernetes, but it's a little bit different in the database domain. So if we apply this file to the cluster, this is what we will get, right? This is what we will get as the topology. Cool. So next, what if I want to upgrade my CPU and memory requirements within the cluster, right? I bump it a little bit. I'm not changing the replicas, right? So I'm bumping the resources a little bit, so it is scaling vertically, right? So what will happen? Maybe in your status app, they just restart the pods like in a rolling update way, and that's it, right? But for databases or data stores like Dragonfly, it is a little bit different. So the logical correct step is that start with the replica first, right? Because the primary instance will always take the reads and writes commands. It will have like the latest data, right? So what we do, we take a replica, we turn it off, and we put it back up with the new hardware requirements, right? Because we're upgrading, we're scaling vertically, right? So we turn it off, turn it on with the new spec, and then the new replica will continue to replicate from the primary instance, until a point that the replica is also, can be promoted as a primary, right? So the logical step would be to deal with the two replicas first. After they're done upgrading, after they're done, having the same data again, then we perform the failover where we replace the primary, right? So before we do that, one of the replicas, because it's already upgraded, it will become the primary. And then this instance is, destroyed and then replaced, and then it will become a replica. So that's just the logical step. Then you need to be careful. You need to code, you need to build that into your Kubernetes cluster for Dragonfly, for Redis, right? It's supposed to have this behavior. So you cannot use the default behavior for stateless applications, right? So that's what we do. Another example is that if I say I just want to have 5 replicas, again, 5 replicas in Kubernetes cluster in the Dragonfly domain, it basically just means one primary with 4 read replicas, right? So this is an easier example where we just spawn 2 more, pods that has the spec, and then they start to replicate from the primary, right? So your Kubernetes operator needs to be capable of doing all the things, and you need to code them like specifically for that piece of database or data store that it is managing. Cool. So that's about, the in-memory data store. In the primary on-disk data store domain, there are like many operators as well. One of the, one of the most famous and most popular one is called PGO. It's from a company called Crunch Data, right? So I'm not going to show more details here, but as you can see, they put the diligence into coding such an operator, right? So that by using it, you have a super powerful tool within your Kubernetes cluster to manage your Postgres, right? Things like storage configuration, right? Things like, if you want your node, like your process to be affinity with some of the host CPUs, stuff like that, and security, of course, right? So they're very like feature rich, and people do put in time developing those operators normally in Go, yeah, as kind of as an extension for a cluster. Cool. And yeah, is there like a unified Kubernetes database control plane, right? So I've been encountered this thought as well, right? Like we kind of need to, on one hand, those operators are so feature rich and they're so good, right? But on the other hand, because each database is a little bit different from the others, they want different things, they want to be managed differently, right? So is there like a unified like platform for that, right? So there are some of the projects. One of them is called Kubeblocks, and yeah, it's they claim to be a cloud native data infrastructure project. But if you look at their GitHub repo, you kind of can tell that it supports many databases like MySQL, Postgres, like MongoDB, like Redis. It also supports streaming platforms like Kafka, Pulsar, right? Vector databases for AI, right? And like search engines and analytics, but they are actually individual Kubernetes operators that the team, the company, and the organization put effort in each one of them, right? Just to make it so good, so that you can take it for granted. Like one day you want to use MySQL, the other day you want to use MongoDB. Like, this thing can handle them all. Um, Personally, I would say that for a platform like this, maybe for each of the individual databases, it's not, as perfect as the others, but this gives you a chance to manage like many of them using one tool, right? So it's quite awesome as well. Cool. So with that said, should we just throw every single databases into Kubernetes, right? This has been like in debate, I think, for a long while, right? So um, I like Kubernetes and I'm learning. I think I'm gonna get my first certificate soon. But on the other hand, I think it's case by case, depending on like your use case and depending on like the database itself as well, right? For instance, let's look back again, the Sentinel. Again, Sentinel is a high availability solution for Redis. It can be used for Dragonfly as well because of Dragonfly's compatibility, right? So it may sound like very simple, right? When a primary dies, we just pick a replica and do a failover, right? It is just that simple, right? But actually underneath, how does Sentinel decide which replica to fail over, right? Don't read the text, but here's an idea, right? Like Red Sentinel takes like a few lot of criteria in like conditions into consideration to determine which replica is the best candidate to fail over. So it is not that easy, right? If we deploy if we develop an operator and we pick like a random replica to fill over, that's kind of okay, right? But if you want to match this behavior, this behavior comes from the Redis experience, right? They come from like they've been doing this like forever. They know what's the best candidate to choose, right? So if you want to match this behavior exactly 100%, it takes time. It takes effort to polish your operator to behave it like this, right? So that's one example, right? So is really can the operator like replace whatever tools existing in the ecosystem? We better evaluate that, right? Another example is about speed and performance as well, right? So, Dragonfly is in memory, so the system is very sensitive to smaller things, right? So we know that containers, they're awesome, they're good, right? But it's still a very thin layer of abstraction there, right? So there are some costs that you're paying, you're probably not aware of, right? So we did some benchmark. Unfortunately, I don't have the number for the exact same machine, but this can give you some idea. So on this AWS C6GN 16x large, Dragonfly can get 4 million QPS on that machine, bare metal, right? If we do like this machine, 8x large, which is half size, but it's containerized, then we get 1.3 million. You can see that we like pay a little bit of premium because of the abstraction, right? So for in-memory, because Dragonfly needs to serve this amount of traffic constantly, and every single one of them needs to be under 1 millisecond. Roughly, we return like 600-ish microsecond, right? So this thing is very sensitive if you add a layer like under it, right? But for on disk databases like Postgres, maybe it's not because most of the time will be consumed by disk accesses, right? So it won't be as sensitive. So probably totally fine, right? So that's another consideration. And finally, I have an example about use case suitability, right? So we recently have a blog post by one of our engineers, Andy. He explained like why Dragonfly, within Dragonfly, when we want to build our cloud service, Dragonfly Cloud, right? So we didn't use Kubernetes for good reasons, right? So in the blog post, Andy explained why that's the case. But mostly at the moment, Dragonfly Cloud, our cloud offering, we use this dedicated model. So you come to our console, you pick like what kind of, how much memory you're going to be using, maybe 100 gig, right? And then we provision that for you. And because we want to give you like the most performance out of it, right? And we want you to connect directly to your instance. So no proxy, no like multi-tenant proxy in there, that instance is basically yours, right? And that machine hosting that instance, the size is decided by like how much memory you pick as well, right? And normally we deploy a dedicated VPC for that as well. So all those things combined, you see that we still do need the control loop, the concept from Kubernetes, but our requirement, it seems similar, but it's actually very different from, what Kubernetes offers, right? So if we try to go with that, we actually see, we're like not using the best parts of Kubernetes. That's why, in Dragonfly Cloud's case, we decided to build our own kind of version of control loop, right? So that's why we didn't use Kubernetes as well. So it's about the use case suitability, right? So if you take all these factors into account, yeah, then you can probably make a very good, informed, educated decision if you want to throw your database on Kubernetes or not, right? For instance, because Dragonfly, we're trying to serve like all the customers, right? But if you're using Dragonfly internally for yourself, then the operator and the performance, degradation probably totally acceptable for you, right? So yeah, so there's no still like we've been all these years, there's no silver bullet to solve every problem, right? Maybe one thing that can be, they can always solve a problem is add a layer of cache. So Dragonfly is a good example where you can add a layer of cache for your backend application. So yeah, cool. That's all I have for today. And if you're interested in Dragonfly, the project, please visit dragonflydb.io. We have a special community page where you can join so that you can get like exclusive content. And if you want to connect with me, I have my LinkedIn uh, QR code here as well. If you don't know how to do it, take your phone and do the search bar, and then the icon will appear, and that's where you scan. Cool. I hope you enjoyed it, and yeah, that's chat.
Yeah,
All
so
right. Thank you. Thank you so much, Joe. Yes. First question.
yeah, so this is more just uh adding to Joe's commentary on the complexities of running a distributed data platform in Kubernetes. One of the things that most folks get wrong when they first try and run distributed data platforms inside of their Kubernetes environments is they're not thinking of all of the failure states and the default behavior that Kubernetes induces in the event of a failure. So let's use Joe's example. You have one primary and two replicas. Ideally, those are not running on the same Kubernetes nodes, because if they are, if that kube node goes down, you're losing multiple instances of your distributed data platform. So now you're in a situation. Awesome. Thank you, bud. So that's my 4-year-old who's very excited. I remember when I was holding him as a baby on one of these. So if you imagine, okay, Kubernetes is, let's say it's a regular deployment and you just have coded it in such a way that it's going to try and bring up new pods. Well, when might that need to happen, or when does Kubernetes shift workloads? When resources are constrained and you're adding new kube nodes, right? Let's say you need to scale up your Kubernetes environment so that you can accommodate more pods, because maybe you're not only running a distributed data platform in it, maybe you're running application instances and other tooling and things like that. Well, Kubernetes is on its own working to move workloads around so that it best takes advantage of the available resources. But the intent to intentionally distribute your primary and replicas so that they're not co-located on individual kube nodes is in direct conflict with the default behavior of Kubernetes. And this doesn't get into the persistent storage, which there's like, you could have a whole religious war over persistent storage and how to attach persistent volumes within a kube environment. But the other piece to mention, I think Joe did a really good job of articulating this, sort of the difference between like a platform specific operator and a more generic operator, is the election process of what to do when something fails. If I have a Dragonfly replica that fails, and the Dragonfly platform has a preference for which instance or which primary or which replica to assign the primary role to, based off of characteristics, where is it in its current sync with the latest known primary state, etc. That's going to vary in a way that is differentiated across platforms. There's also a very sneaky challenge in how do you inform a distributed data platform that presumably can run outside of a Kubernetes environment, how to be aware to not put, like, I don't know, let's say topics, for instance. If you want a certain distribution or to not co-locate specific workloads on specific compute instances, how do you, in the application layer, differentiate where you put these data sets so that they're not running on the same Kubernetes node? So like the problem that Joe's talking about is we don't build distributed applications with an awareness of the underlying infrastructure layer. And we do that intentionally to make it portable so that you can run it on different types of platforms. And usually we use the networking interface to stitch together a cluster.
And you said we. Who is we?
We is like everybody who builds distributed data platforms.
Right. Okay.
Yeah. I work at Elastic and I talk to people about this because we're a distributed data platform, but the principles are identical in Dragonfly and Redis, etc., where you have primaries and replicas for increasing read performance and resiliency of data in the face of, like, we just assume some future failure state of an individual instance of that running process, whether it's in a container or a virtual machine or a bare metal server. And so having the ability to run a distributed data platform just solves a huge number of headaches and like keeps your app from completely becoming unavailable, all that sort of stuff. But the moment that your database layer, there is an assignment and there is design decisions that make assumptions about where data is and where data is not, and you decide to run that inside of the context of Kubernetes, now your runtime does not have a direct association with your compute and your storage, etc.
Right. So Joe,
because we've introduced the abstraction layer.
Right, right. Interesting. So that's Joe, do you can you address that really with the bare metal, right? You showed that it's able to scale and it performs better on bare metal. And then you are able to run it in Kubernetes, Dragonfly this is. How does how do you do that? I mean, how does it know that it's in Kubernetes and it performs differently and how does that work? Did you know the do you know those details?
Right. Yeah. First off, I want to ask you guys a question. It was my camera off the whole time, like when I.
Oh, it may have been, but I mean your slides were great. So
Oh,
I
I
was just
see.
looking. Yeah, yeah, yeah.
Cool. Yeah, because I lost the dog at the beginning and I replugged it. That might be why. Right.
Okay.
So
Were
yeah,
you really animated like this?
I was like on my variety show like this, but
Oh, we missed it. All right, man.
anyways, yeah. So for I guess your question is about the performance, duration in terms of containerization, right? Or
And how does it know? How does Dragonfly know it's inside of a container? And what does it do when it's in there? Does it turn
right,
off something? But yeah, that's
right, right.
I think
So
that's what we were that's what I latched on to most.
I see,
So
I
yeah.
see. So I don't think Dragonfly is aware of the environment in that sense. These numbers we just got by benchmarking Dragonfly directly on the machine versus a containerized environment, right? And I've been told, I'm not 100% sure, but I've been told by engineers that nowadays, with the container, with the capability of Kubernetes, um, the number, the performance here, like it can be like really, really close. Like we don't have to pay such a huge premium anymore. But I don't know how and why. Yeah. And just to add a little bit for Dragonfly Cloud, why we are not using Kubernetes are mostly the other reasons. Like, when a customer come and they want, say, an instance of 100 gig, we need to make a very dedicated, that machine. We provision it exactly the way that the customer wants, and then we put Dragonfly on there, right? And then we probably deploy a dedicated VPC in there as well. So those requirements are kind of not matching what Kubernetes is the best at. That's mostly the reason. Performance is one reason, but it's very close right now. I heard it's not a determining factor anymore.
Very interesting. So you have a cloud offering. Dragonfly is a cloud offering. Do you run
Yes,
your cloud offering bare metal or do you run it in Kubernetes?
we run it bare metal, so we have our own control plane that that does the conciliation thing, all the steps, make sure that, say, if you ask for instance, we give you an instance and we don't give you two instances, right? Like we give you exactly one with the spec, with direct connection with VPC. So we have something in Dragonfly Cloud that we build in-house that uses the control loop concept and idea, but but it's different from Kubernetes. Yeah.
Yep, yep. Um, so the Sentinels, Dragonfly has its own Sentinel. Is that correct?
No, so Sentinel is a project by Redis.
Okay,
It's a Redis instance running in special mode that does the monitoring and failover job. It doesn't provide data manipulation. Only because Dragonfly is highly compatible. So if you put Sentinel in front of Dragonfly, that works as well because of the compatibility. Yeah,
okay,
like this, I believe. Yeah, like this.
okay. I have one question which is kind of general. So can you have two Sentinels?
Mhm. Yes, the Sentinel itself can be a cluster. Normally we go with like an odd
Okay.
number, right? So
Yeah. Yeah.
three node Sentinel cluster, all of them, they don't they don't they all don't provide data manipulation. They do the Sentinel work and they provide HA for themselves. They have the election process as well if a Sentinel instance goes down, right? And yeah, so this can be a cluster.
Excellent. All right. Thank
Yeah.
you.
Hi,
So are there other questions? Yeah.
this is Gopi. I think I asked earlier, uh, just a question with respect to the database like MongoDB.
Mhm.
Are they kind of incorporating what Dragonfly is doing within the database itself, making Dragonfly kind of redundant?
Uh, right. So I think MongoDB is one of the pioneers of NoSQL, right? So it's designed to have they also call it replica set, right? So they have redundancy, and then you can have like sharded cluster on top of um, the what is it called? The replica set. Dragonfly or Redis or Voki, depending on your tolerance, because it's in-memory data store, right? So depending on your use case, if you're purely using for caching, then maybe one instance is enough. If it goes down, then it will come back and you need to re-warm up your cache. For some case, that's not ideal. That's why we gradually added functionalities like replica to make it redundant. Um, that does that answer your question or not?
Uh, kind of. The question is some of the features like what the Dragonfly is providing, can it be embedded in the database itself? Is that the direction it is going? Is kind of where I was coming from.
So
Um,
Gopi, I think it's definitely a really good question because if you can get away with not running a cache layer,
Right.
then your application architecture is probably simpler and you have a bunch of cache writes and cache purges that you don't have to think about because you don't have a caching layer anymore. Typically, the reason why you would use a Dragonfly or similar platform is because you have a transactional load at the you have a transactional load from like your first party code, like your, let's say your middleware service that exceeds the throughput potential or that subverts the right assumptions in your database layer. So if you have an incredibly high transactional load where the same data set is going to be consistently referenced throughout, say, a user's session in a web application, it oftentimes makes a lot of sense to have a principal data store in something like a Mongo, something like an unstructured data platform. That's what I talk about all day, or an RDB, and then a caching layer that is referenced first, and upon a cache miss, a secondary operation goes and retrieves the necessary data from your principal data store and moves it into the caching layer. And the reason that this is such a common pattern is because when you have consumer facing applications, like the whole internet can use it, maybe you have a mobile application or whatever, the principal data stores tend to focus very heavily on uh, atomicity or acid, adhering to acid principles, on data resiliency, on data immutability, on version control and auditing rights and things like that, where that induces a fairly substantial workload from just a data management standpoint. Like that's a lot of work for a single write. Somebody types a note into like a notes field. Yeah, you need to commit that somewhere where you're confident that it's not going to go away. But then you have this other problem of your web interface needs to be snappy and responsive, so it doesn't take, time. And so, yeah, in a lot of cases, you can just scale the principal data store. Mongo is a horizontally scalable unstructured data store. There's a lot of those out there, and I have a bunch of customers that do that. But from a cost standpoint, in a lot of cases, as the size of the data set scales linearly, the cost to scale the data platform horizontally to maintain let's say like a query SLA, the cost will actually scale like exponentially. So by introducing a caching layer, you essentially flatten that cost increase curve, because your cache layer doesn't have to grow linearly with the size of your overall data set. It needs to be sizable enough to be able to accommodate, let's say, your like maximum total number of concurrent users. So that's really the purpose behind a caching layer like Dragonfly. And I think there's a lot of organizations that sort of immediately dive in without necessarily understanding what what the capabilities of their principal data store are. I've worked at multiple companies that desperately needed a caching layer that didn't have one, and it introduced a lot of tech debt and sort of like architectural impasses in the data architecture layer or the query behavior that prevented the application from being able to realize features that were like critical to users.
Yes, and I've seen
Yes.
that too. Yeah, Joe, go ahead.
Totally agree 100%. So, right. So as the purpose of caching layer, caching layer is everywhere. Like your CPU has like 3 layers of caching, right? So the idea is that you put the hot, frequently accessed data in memory, like a tweet from Justin Bieber, not a tweet from me, right? Then everybody reads, we check Dragonfly first, right? And we see that tweet in Dragonfly, we can respond that like very, very fast, right? And it never hits the primary data store after it's written. Yeah, so that's an idea. But on the other hand, why we just don't cache everything, right? Because memory is like 10-ish times more expensive than disk, right? So there's a tail, like there's a long tail effect. You want to use the resources like wisely, use like right? You have like 1 PB data on disk, but only 1 T, maybe even 1 gig is the most frequently accessed. That's where you put the data, in here. And it also depending on the strategy of a project of an organization as well. I think for Redis, they've been spending a lot of effort making it super resilient as well. So I'm not sure right now. I think, but like the few years ago, Redis Cloud, the company, they tried to promote Redis as a primary store, right? Um, so yeah, it definitely can handle some of the primary database use cases. But remember that in the end of the day, systems like Redis and Dragonfly, we don't have write-ahead log. We probably have write after log, which means that you still risk your data being lost. Like it's in memory but not flushed yet. It's totally, possible. So yeah, we Dragonfly at the moment we don't try to promote ourselves as the primary store. It's more of a auxiliary system that can speed up your application, and yeah, and it has like high, I would say, upper limit in terms of how it utilize your CPU and memory. But in terms of persistence on this, I personally recommend you to write it into Postgres.
Right, right. Is there a limit on the object you can store? What is the typical size constraint?
Right. So in Dragonfly, the it's limited by how much memory you have on the machine, right? So, but on the other hand, we also it's common to Redis and Woki and Dragonfly. like if you cache a blob, say like a few KB, maybe 1 meg, a few megs, that's gonna be fast. But if you're caching like a whole movie in there, then that won't work properly. That one single blob is too long. Yeah, so normally the JSON payload, we see in like regular software development, they should be good to be cached or to be stored in Dragonfly. So really the upper limit is by the memory of the machine. But um, uh, Redis has like 7, 8 evacuation policies, which means that if your memory is close to full, you can choose like a strategy to evict keys that probably are not frequently accessed, probably not recently accessed, right? So it can keep going. We have something similar. So in Dragonfly, we have only one policy. It's called the cache mode. So once you enable that, we have an algorithm that determines which items are more valuable to be kept in the memory, right? And some of the items are less valuable, maybe a tweet from me, then after a certain period of time, the key maybe get evicted. So with that
That's
said, then right, as a caching layer, you can go forever.
that's
Um,
interesting. Well, what is that strategy? It's called,
so
so it's not like it's not least recently used, it's
right,
something else. It's
good question. That's a combination of LRU and LFU. So
okay.
right, we have like I personally work a lot on our blog post. I like this page of blog posts, so please do check them out. One blog post before I joined Dragonfly by our CTO is called Balanced versus Unbalanced. And in here, Roman described the algorithm called, um, no, sorry, that's not the one. That's for snapshotting. The cache design, Dragonfly cache design. So this one, Roman described a algorithm called 2Q, right? So
2Q.
2Q, it's not something like super young. It's based on a 1994 paper, but people just don't find the lost gem, I think. Right.
Yeah,
So
right.
it has a strategy. It's a combination. To put it simple, it's a combination of LRU and LFU, so that we have like the probationary buffer, and maybe if the item get hit again, it get promoted, right? So it's not we cannot run an AI program in this image store, at least at the moment, because it needs to respond to your request sub
Yeah.
millisecond millions of QPS, right? So we cannot have a model in there. But as you may know, some of the algorithms they don't have to be as complicated as an LLM, but it's super efficient. This is the one we discovered to help you evict memory when it's close to full.
Yeah, this is great. And actually some Java JVMs that they use something similar to this now that I see it.
Right, right.
So this is you're for
Yeah,
the garbage collection. That's how they do it.
yeah.
Okay, this is
One,
nice.
sorry.
Thank you.
Yeah, no problem. And another thing I want to add is because we're talking about what do we do, what to cache, like what do we do if the memory is what's the limit, right? So let's recap. The limit is how much memory you have on that machine. But if you enable the cache mode, then because your keys are automatically evicted, then you kind of have unlimited space if your data is like if we care only about the hard keys, right? So that's one thing. Another thing is that we recently introduced another feature, is currently experimental as well, called the SSD tiering. So basically, if this is enabled, then what happens is that we will decide, I guess similar idea, we will decide that some of the keys are less valuable. So we offload them to the SSD. So it's on disk. And this is different from snapshot backup, right? So it's just a way to save the valuable resources, the
This
memory.
looks like paging, right? When you're yeah, right?
Yeah, it looks like swap, I would say, but
Okay.
right? But based on our benchmark, it's still like super fast
Oh,
speed.
that's a good. Actually, go
That's a
back to
good
the
thing.
table. This
Yeah,
one's nice. Yeah.
I like
Okay.
it. Yeah. So talking about cache, your CPU has caches. Uh, why we don't use all of them? Like why we don't use them like this everywhere? Because they're super expensive, right? And that's why they're small, but they're fast, but they're super expensive, and they're closest to your CPU. The caching layer we are talking about in terms of like a in-memory data store versus an on-disk store is this layer, right? So Dragonfly operate um, in RAM and Postgres, for instance, operate on disk. But you can see there's still like a very significant price difference and speed difference, right? Yeah, that's why you keep the hot data. It's the same idea from the top down. Like you keep the hot data, the hottest data to the most expensive medium. Yeah,
They're very nice. Love it.
right. So with this enabled, then based on our experiment, let me see if I can find some numbers, right? Maybe it's not a yeah. Let's say you have a machine that is uh, 28 gig, like you can use all of them as your in-memory data store, right? But if you run Dragonfly in this way, where you say, I want my max to be only 14, but that's enable SSD, right? Then you throw the same amount of keys. That's how much? That's 27 million. You throw 27 million keys to there. Then based on your query, Dragonfly will offload some of the not frequently used ones down
Yep.
to SSD, and to conform the requirement of maximum 14 gig on its machine. So imagine you enable SSD tiering and the eviction policy, then yeah, like your data store is going to be very large. Although obviously, again, no silver bullet. When this is enabled, your throughput is going to go down a little bit and your latency is going to go up a little bit. But based on our benchmark, they're still within the acceptable range. So the average latency still within, I don't remember, maybe one. Yeah, we're still within the sub-millisecond range for the median and average. If that's acceptable for you, then enable it, right? Because it will use much less memory. But if that's not acceptable for you, you need everything, not just the median and average. You need everything to be sub-millisecond, then don't enable it, but you pay more for your memory. Trade-offs, yes, always.
Yeah,
Yep.
there's a really interesting um there's an interesting perspective on ways to take advantage of this type of data tiering. Um, the average uh, the average latency that Joe's talking about is going to have a higher latency time for the first request when the data is on SSD, but Dragonfly will automatically move that specific data into memory as part of the sort of resolution of that first request, because it's changing the last time it was requested. It's going to be recalculated by the 2Q algorithm. Um,
Yep.
and so in human driven applications, like a mobile app or web application where a person is navigating something, there are a number of different ways to interpret a user is potentially going to land in a spot where it would be nice if their data was already in memory. And so you can actually induce something like a prefetch. So if you think about you're logging into like your bank app, well, you could, and let's say they cache things like, all of your account balances and like the account IDs and things like that, because that's going to accelerate the ability of the web application to present to you like your accounts overview page. So you log in, and the first page that you're getting to is going to have that data. And that data lives either in memory or on SSD in Dragonfly. Well, you're going to go through something like a multi-factor authentication process, or an authentication process that involves some type of latency where there's, like OAuth check, or something. If it's an internal facing app, maybe you're hitting an SSO, and so you might have 150 milliseconds of latency in that auth context.
Yeah.
But you've already gotten that username, and you can store a map. You can essentially just fire a query for all of that user's data to Dragonfly, which is going to pull their data up into memory.
Yep.
And then when they actually get through the auth process and they hit the front end web service, which cascades into the requests to the middleware and direct calls into the cache layer, you've already pre-warmed the data into the memory. And
Yes.
so that's like a really convenient way for human-driven applications where the behavior of the app is driven by human activities, because humans are like ludicrously slow in this context, that you can actually fire a request with what you know about that user before they're even getting to the page, so that when they get to the page, it's the fastest possible retrieval, but you're able to stretch the total volume of data that you can store within your cache, because you're not relying entirely on in-memory data.
Yeah, that's a great strategy. I recommend that too for any application or system designers. That's a great strategy. And it works great with Dragonfly, right? That's it. I guess that would be one of your
Yeah, I
nice
would
use
say
cases,
so.
right? Yeah.
Definitely great strategy, totally. And I personally I like this particular blog, and why it's called caching all the way down is like similar idea. Like let's look at this picture again. So as developers, you can imagine we don't have this SSD tiering or eviction feature at all. You just have like a very plain, Dragonfly instance. As backend developer, you can use all the uh, smart strategies that you have for caching, right? Maybe you cache maybe you prefetch whatever the homepage for that user is, and then you do expiration time, right? So yeah, that's great. And now what we have is that we as developers, we're already doing the smart things. And in the meantime, if you enable this feature, then the database, the data store itself is also doing its own smart thing for you, right? Two layers of like intelligence, doing all working together to make the app great. That's how I see yeah, features like this. Even if we don't, then totally fine. We manage, we're backend developers, we manage our cache super confidently, no problem, right? Then with these features enabled, that's another layer of intelligence there, just for you. Yeah, that's how I feel about this. Yeah.
Yes, excellent. Excellent. All right. Any other questions from anyone? Anyone? Um, anything? All right, Joe, anything else to wrap us up?
Right. Again, it's my great honor. I feel, I feel the my talk. I think I did well, but I think the conversation happened afterwards is what really makes the whole meetup, the session shine. Thank you all so much for the questions, for the comments, I'm not sure how to pronounce your name. Is that Thad-
Yeah, it's pronounced Thaddeus.
Thaddeus? Yeah, thank you, Thaddeus, for all the things you say. I learned a lot myself today as well. And yeah, thank you, Paul. Thank you, Judy, for hosting. Yeah, I mean, I think like um, I'm continuously learning. I consider myself like a lifelong learner who doesn't as developers, right? But I do like infrastructure in terms of databases and things related to say Kubernetes and things, because um, I have a feeling that there are many hypes right now, like the AI, like the blockchain, right? But in the end of the day, you need to write down your data somewhere, and you need reliable infrastructure for that. So I think infrastructure, DevOps, databases, these are like the truly exciting sector as well, right? Not maybe I don't code Python for an LLM that frequently, but I appreciate what we all do here. So yeah, I guess that's what I have for
All
today.
right. Well, thank you very much. And yes, the your blog is really nice. I like that. There's a lot of good info. Again, I'll put that into the group chat, and it is on our page. So this will be recorded, and we will upload it to our YouTube channel. And yes, and I will be holding the next we have an in-person meeting. I forget the date, but that will be in Columbia, and it will also be recorded and put onto our YouTube. So that's coming up. So thank you again. Thank you, Joe, and thank you, Dragonfly.
Thank you all. And I will be, yeah, I will be joining more of our sessions in the future for sure. It's delightful to be here.
Thank you. All right. Thank you so much. I will
Bother, I won't get bothered anymore.